Concept learning and general to specific ordering. Concept learning is about finding a rule or function that can classify whether an example belongs to a category or not. Example: given a description of a day, like sky, humidity, wind, determine if it's a good day to play tennis. Input: a set of examples with attributes. Output: a hypothesis that correctly predicts the target concept. For example, play tennis equals yes/no. 2. Concept learning as search. Think of concept learning as searching through a space of hypotheses to find the one that best fits the data. We use general to specific ordering to guide this search. Start from the most specific hypothesis, match only training examples, and move toward more general ones. This hypothesis space forms a search space. 3. Find S algorithm, maximally specific hypothesis. A simple algorithm that starts with the most specific hypothesis and gradually generalizes it to match positive examples. Steps: initialize H to the most specific hypothesis. H equals for each positive example. Update H. If the attribute matches, keep it. If it doesn't match, replace with wildcard. Ignore negative examples. Limitation: works only with noise-free data and positive examples only. Small blue diamond emoji. 4. Version spaces and candidate elimination algorithm. A version space is the set of all hypotheses that are consistent with the training data. It is defined using S, the most specific hypothesis, G, the most general hypothesis. Candidate elimination algorithm maintains two boundaries: S boundary, specific hypotheses that are still valid; G boundary, general hypotheses that are still valid for every new training example. Update S if a positive example is seen. Update G if a negative example is seen. Eventually, the space narrows down to the best consistent hypothesis. Small blue diamond emoji. 5. Remarks on version spaces and candidate elimination. Sensitive to noise, one wrong label can mess up the whole space. Becomes computationally expensive for large hypothesis spaces. Still useful for understanding concept learning as a space narrowing process. Small blue diamond emoji. 6. Inductive bias. Every learning algorithm makes assumptions to generalize beyond the data. This is called inductive bias. Find S bias. The concept can be represented in the hypothesis space and is the most specific one. Candidate elimination bias. The target concept is in the hypothesis space and data is perfect. Without inductive bias, a learner cannot generalize from finite examples. Summary chart. Topic: key idea. Concept learning a rule from examples. Find S. Start specific, generalize with positives. Candidate elimination. Maintain version space, S and G version space, all consistent hypotheses. Inductive bias. Assumptions needed to generalize. Hi everyone. Concept learning and general to specific ordering can be super fun if you combine a storytelling script, relatable analogies, and animated visuals like robots, treasure maps, and classroom scenes. Here's our animation ideas for each concept. I'm Robo, your curious little friend who wants to learn just like you. Today, we are going on a learning adventure to find out how machines learn new things just like students in a school. Let's say I want to learn when it's a good day to play outside. You give me some examples. On sunny days, we play. On rainy days, we stay in. Over time, I notice a pattern. That pattern is called a concept, a rule that helps me decide. Finding the right rule is like searching through a big library of ideas. There are thousands of possibilities, but only a few match all the examples you gave me. So I search from the most strict rules to the more general ones, step by step. Now let me show you how I use the Find S algorithm. I start by saying, I know nothing. I'll assume only exact matches work. Then each time I see a new positive example, I slightly relax my rule by saying, okay, Maybe I don't care about humidity. I'll allow anything there. My brain keeps 2 pages open, one for very specific rules, things I am sure about, one for very general rules, things I think might work. This notebook is called the version space. It contains all the rules that still make sense after seeing your examples. Now it gets exciting. You show me positive and negative examples, and I update both sides of my notebook. I remove rules that don't fit the new positive examples. I eliminate rules that wrongly accept the negative examples. Little by little, my notebook gets smaller and smarter. Sometimes, there's no perfect rule. So I use my brain's built-in preferences, called inductive bias. I might assume the simplest rule is best or only the rules I already understand. That's like how you might guess the next number in a pattern because it just makes sense. Narration. Let's wrap it up. Here's what I learned today. 1 keycap emoji. Concept learning equals learning a rule from examples. 2 keycap emoji. Find S equals I start strict, then generalize. 3 keycap emoji. Version spaces equals my smart notebook of rules. 4 keycap emoji. Candidate elimination equals use yes and no examples to narrow things down. 5 keycap emoji. Inductive bias equals my built-in thinking preference to guess smartly. Learning is fun, especially with the Robo by your side. Thanks for learning with me. Want to join more AI adventures? Don't forget to like, share, and subscribe to Gyann. Let's keep learning the smart and simple way.